We're recording.
Yeah, all right. Thank you for coming. This is our first time in person this year for the New York Comic-Con side. We're very happy to have Kerry to teach us about more on the rock burning on key caterpillars. All right, so all yours.
Good away. All right. Thank you. This is joint work with Danielle Cox and Parker Ella Messenger. All right. Feel free to ask questions. Let's see. Why isn't it going now? Oh, there we go. Good. Okay. All right. So I'm going to describe what graph burning is. Describe what the Burning Number Conjecture is. Everyone abbreviates that BNC. And then I'll just give our work. And it includes 3 bad dreams. Okay. False approaches. All right. Let's see. So, okay. So let me tell you what graph burning. I'm not sure if any of you have seen graph burning. Or it's a simple little process. It's supposed to, in the first paper sort of says it's like the spread of a meme online. Let's, for example of it, the process, and every round, anything which is already burns, think of burning the vertices. When I burn so the entire graph is burned. Burning, just marking it with a red or something like that. And then the first we do in each round is you spread to any new vertices, then at the end you choose a new source. So the first round, nothing has been burned. And you choose a new source, 1. That's 1 round. Next round, from 1 it spreads to those 2 neighbors and choose a new source. End your round 2. That's end of the second round. And the third round, these right here spread there. The ones from a 2 spread there. You choose a new source, 3. So it took you 3 rounds to burn the graph. So we said the burning number is 3. Burning number is the fewest number of rounds you need to burn the whole graph. So burning number of P9, half of 9 vertices is 3. Let me do another example. Say P5, half of 5 vertices. So suppose you first pick that vertice 1, first round, second round, from 1 it spreads to those 2 neighbors, you pick source 2. And in the third round, it spreads everything, but you always, just to keep it accounting, we always choose a final source. So even though everything's burned, I choose a final source 3. So that's right. So it still takes 3. So burning number of P5 is actually still 3. And you can see how with just 2 times you couldn't actually burn the whole graph. So it's a bit redundant to wind up over burning the same thing with the same fires, but you still need 3 to burn the whole thing. Okay, but in fact, right, the way I like to think of it is covers. So even though someone may have just walked in, you will not be at loss because everything we'll talk about here will be in terms of covers. Okay, so in fact, with the first example, P9, what did the first source burn those 5 vertices, right? The second source burned those 3 vertices, and the last source burned them. So the later sources burned less. So in fact, you can think of it just a cover problem. I'm covering it with distinct balls with distinct radiuses. And I want the maximum radius to be as small as possible. So in fact, you can think of the burning number as just a maximum radius plus 1. See the example here, the maximum radius ball is a radius 2 ball, centered right here. Radius is 2. And the burning number, remember, of the P9 is 3, so it's maximum radius plus 1. And notice if you look at P5, you're still stuck. You can't do it with just a radius 1 and radius 2 ball. A radius 1 ball would cover 3 vertices, and your radius 0 ball covers 1. You just get 4 vertices, so you still have to go up to radius 2. So in fact, the burning number you can see by covers. So this, and the way I'll talk about this, I'll forget the initial description. I'm always thinking of covers. So just thinking of, you have a graph. Cover it with balls of distinct radiuses, and you want the maximum radius to be as small as possible. And so the burning number we say is that maximum radius plus 1. Feel free to stop with any questions. Small group. Okay. So burning number of a path. We saw everything is rounded up. They don't say so. So for example, burning number of path Pn is square root of n. We saw that in an example before. right? For example, P9, square root of 9 is 3. For 5 also, square root of 5, 2 point something, round up, 3. So, and generally to sort of see that for the path, square root of n, burning number. And here's the big conjecture. So the whole big conjecture for this question, this topic, is the burning number conjecture, BNC, is that in fact, the conjecture is that for every graph, square root of n is sufficient. It's been worked out for a number of families. For a lot of families, it's well less than square root of n is enough. Like for example, a star, 1 and it all burns. There's a lot of graphs that burns much quicker. But the bound is this, and you can sort of see why a path seems like one of the worst things. It's a spread out, has to go all the way down the path. If it's more congested, you would imagine you could do it in less. So conjecture seems kind of reasonable. First paper, this was introduced, first published journal paper introduced is these guys, Anthony Bernardo and students and some other folks, 2016. Did some bigger results. It's close to being proven. It's really close. So asymptotically, like, you know, a little constant, so you have a little constant to the square root of n. So it's really close to square root of n. So everything about this conjecture, getting even just a few off, you're not really very close. You want to get, so the goal now is to really get right down to the burning number conjecture, to get it exactly. And there's this thing, all the 7-author paper, like you guys 7-author paper, at least 4. If all the degrees are at least 4, ends up sufficiently large, and actually it's true. But so there's a number of results getting it under certain circumstances and whatnot. It's other results of the storm form. Okay. So, but in fact, the thing is, this problem is basically all you need to focus on is trees. Okay, so I think it's sort of, in fact, the burning number of any graph is just look at all the spanning trees, pick the best one, pick the one with the minimum burning number, and that works. You can sort of see why that works. Sorry, Zoom people, I'm going to write on the board. I mean, if you have a graph, and you're burning it, if you take out an edge, just makes it harder for it to spread. Makes it harder for it to spread. So taking out edges, taking the spanning trees is going to make it go up higher. And in fact, you can show that it's, for a graph, it's equal to the spanning tree. So what this means is you can just focus all your attention on trees. So all the action happens to trees. So all we're looking at is trees. That's gets a whole question for you. And we're going to look at particular pea caterpillars, which are a kind of tree. Pea caterpillars. So the P is just an integer, 1, 2, 3, 4, whatever, and just means a pea caterpillar is this. Take a path, a maximal path right here, called a spine, and just hang trees off of it. So, like for example, here's a height 1 tree, a height 2 tree, and so on, like this. Hang trees off of it, and the P refers to the maximum height. So this, for example, this is a 2 caterpillar because every tree is at most height 2, distance 2 from it. And so, notice every tree could be described as some kind of pea caterpillar. So we're sort of in the ballpark of the whole problem. And BNC is true for, it's going to be true for 1 caterpillars and 2 caterpillars, and not beyond that. Yes, it's proven for 1 caterpillars and 2 caterpillars. Various 2 different groups proved this a few years ago for 2 caterpillars. Okay. So what about bigger? So for example, just here's an example of a 3 caterpillar. Oops. Got it there. 3 caterpillar, right? All the non-spine vertices are within distance 3 caterpillar. And you can see you can do this one with is it 4 balls, for example. This is a radius 1 ball, radius 0 ball, a radius 2 ball centered right there, and a radius 3 ball, because it takes biggest radius ball is radius. So you can look at that, it does get everything. Everything's within distance 3 of this, right? 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on. So biggest radius ball is 3, so the burning number of this one is 4. To prove that that's the best. Okay. Okay, so this is sort of what we're looking at. It's caterpillars and go. And here's our main theorem. Okay, main theorem. This for any fixed p, so pick p to be any your favorite constant. Let's say for sufficiently large n, the BNC holds for all such p caterpillars on n vertices. And in fact, you can take the n to be, this is far from optimal, but here's an n that works. So take your, okay, so what this means is we haven't got the full BNC because you take your p to be, say, 7, we can prove it for infinitely many, all but the first, these small caterpillars. You're missing these small caterpillars. Okay. All right, so that's the theorem. And actually, that's the whole, so I'll say, warning, I guess a lot of talks these days are like, a bunch of results. This is it. The one result is here. The rest of the talk is me explaining that one result. I feel like this, I gave this talk a month ago at Brascan, and it maybe a bit more for them. It's like, okay, guys, you guys are really into this. Here's some tools you can use if you want to prove the burning number conjecture. Some of them want to prove it, so maybe it's useful. Anyway, the rest of it is just me describing the proof of this one theorem, All right, so from a bird's eye view, what is the proof? And I'll try to give us a bird's eye view of it. I mean, not with all the details, but I'm trying to give you a sense of the main points of the proof. So the caterpillars I actually draw would be really, really simple one, but the idea is generalized. So here's a caterpillar, right? It's a one caterpillar, but imagine any old caterpillar. And our strategy is this. We take this caterpillar, which we don't know about, and we're going to convert it into a path by taking all these vertices off the spine and push them over here to the end. So I took these 3, pushed them to the end, and it was a bigger caterpillar, just push them all to the end. Okay, so convert it to a path. And what's the good of that? Well, paths we know all about. Paths, we know exactly what the burning number those are. Here's my path to do the same number of vertices, and I find a cover of the path with some balls. Notice this is a cover of the path with some balls. And now I want to use that cover to go back and cover that one. So we could describe this. In this case, you can see how you can go from this cover back to a cover that's sort of redrawn this. Let's see on the next slide. So here's that path, and here's that caterpillar, which is now doesn't have those 3 vertices. You can just rearrange the balls to get a cover for this. I just take the let's say take this yellow ball and put it to the front right there, and I push this blue ball forward, and this pink ball is sort of shifted over a little bit. And you can see that this is the same balls cover the caterpillar, right? So this is radius 2 ball here, this radius 1 ball centered there, this radius 3 ball centered there, radius 0 ball. Please, anything doesn't make sense or small, feel free to ask. Oh, this is just random. Yeah, we're gonna get to the paper has to give a well-defined strategy. Yeah, right. That's all. That's the hard part. Yeah, right. So we described our sort of the outline of our proof is like this. We go from unknown to known and back. So we tell the caterpillar we don't know about, that's the unknown. We go to a path. We create a path of sticking all the vertices at the end. Now that path we can cover with square root of n balls. Great, recover the path. And now we want to convert back. We have to have a good strategy, as you were saying, a nice way to get back to it. So we want to convert this to what we call a spine cover of the original P caterpillar. By spine cover, I mean, in fact, you notice for most of these, the balls are all centered on the spine. I'm never going to put balls, and this would make sense here, but say the bigger P caterpillar, you might imagine putting balls down on the spine. And if you want to really prove the BNC, probably need to do that, but we don't get the full BNC. All of our covers, all the balls, centers are all on the spine. So centered here, centered here, centered here, always centered on the spine. So, okay, so this is the rest of the talk, is basically saying how do you do this? How do you go from a cover on the path using the same balls to get a cover the P caterpillar? And since this was only square root of n balls, this is only square root of n balls. So just the same number of balls. So we've got the BNC then. Notice we don't get an optimal cover. We're just saying square root of n works. Maybe the case of this P caterpillar can do with much less balls, but we're just saying that square root of n works. Okay, so we do the same balls, just rearrange. So that's just going to rearrange the balls. All right. So, all right, here, a bit of a messy picture. Just to get another outline of sort of the proof, we're going to do is, again, we start with some caterpillar, and we create this path. So the path I'm going to call T0. That's where we start this process. And the root vertices, maybe I should say just this. So you have your P caterpillar, and you can think of as trees. I'll just draw them as paths, because really the paths are the hardest things anyway for us. You have paths hanging off of your spine like this, and we call these spine. We call these vertices, which are the roots of these trees, we call them root vertices. So we have x1 as a root vertex, and x2, and we start left to right, calling these join here, and so on. We call these our root vertices. And our goal is to rearrange the balls so that on the slide so that those are covered. Notice back at this, right? These are the root vertices. X1's covered because it's the tree, all the vertices in that tree are covered. X2 is covered, and X3 is, we say tree covered sometimes. So our strategy is start with T0. We sort of know where it came from some caterpillars. So we even though there's no T0 is just a path, we sort of remember, oh, X1, X2, X3, and so on are the root vertices. That's where the trees were hanging off. And we're going to sort of go step by step from left to right, trying to rearrange the balls to cover root vertices. So T0 is a path. T1, we take the stuff we moved over, put it back where it was, back there, rearrange the balls a little bit, and we cover X1. So get that was taken care of. Then we take the vertices we moved over there, put them back to X2, rearrange the balls a little bit, and cover X2, and so on. And if we do this right, at the end, we've covered, at the end of the process, we've actually gotten our whole caterpillar. That's our sort of rough process, start with the path, step by step from left to right, dealing with the root vertices one at a time. Okay. First, I promised 3 fall streams. First fall stream, we're doing a proof thing. This is some cheap approach that works. So one cheap approach, you think, just move the legs one at a time. Just take, you're thinking of doing this, just one at a time, do each leg, and you always have a good rearrangement. There's never going to be any problems. So let me just shatter that dream right away, and give it also a nice little example. So in the process, what we're doing is we always look back at that process, right? We go from, 1 to having 2 to having 3 to having 4. So in the middle of the process, imagine you were right here and you've gotten great. You're like, great, I've covered 3 of them. If I go, and this spine has 9 vertices, and here I've moved one of those over to there. So this is like in the middle of that process. I've moved one of those at the end over to B6 right there. And if it was an easy thing to do, you just feel like I can always just rearrange the balls to get that. In fact, let's do it the heck of it to see you cannot, even though this takes these balls. The biggest ball there was a radius 2 ball. It's a radius 2 ball there, a radius 1 ball, and a radius 0 ball. And actually cannot do this. This needs a radius bigger. Let's just exercise that one right here. So if you do write this out, so we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Well, notice that same number of vertices just rearranged this, and notice there's no overlap, exactly cover. So if there's any overlap, you're not going to be able to cover this. You can't waste it all. So let's look at where the radius 2 ball can be. Well, if the radius 2 ball is centered at V3, and we'll get one, this one right here, we get this 1, 2, it would get, let me write it over here maybe, it would get out to center it at B. So obviously centering it here, centering it to V1 or V2, you're going to not cover enough. Notice how many does it cover here? Here it covers 1, 2, 3, 4, 5, 6, 7, 8 vertices. If you don't cover 8, but your ball radius 2, you haven't been as efficient as possible, you're going to lose. So you can't put it here, and you only get 1, 2, 3, 4, 5, 6, 7. It's the only places you could conceivably have any hope of doing it here would be at V4 or V5, the only place you could center the radius 2 ball. Okay, well, the problem is you can center it, and they're symmetric, so it doesn't matter which one you think of doing that. So suppose you go to V4. Put it at V4. Well, you get 1, 2, you get 1, 2 out there, 1, 2. You stop at that one vertex there, it must do a 0 vertex there. Look at what happens this way, though. You get 1, 2 this way, 1, 2, 1. You wind up with these 3 left over. So we center it at V4. Whoops, you get 3 vertices, which the radius 1 ball only covers 3, but they're spread out in a bad way. And that's the only option. But the only option was either V4 5. Okay, so in fact, you can't do this. So in fact, you can't simply always move 1 and hope you can always do it. You need to have some conditions under when you cannot rearrange the balls. So that's the first ball stream. You have to have some conditions. You can't just always do it at every step. To enter the first stream. Okay, so we bring in special operations. So we have to be careful about how we rearrange the balls. Okay, so here's an operation on the balls. And I've sort of drawn this spine. Often I don't draw the stuff hanging off of it because all of our balls are centered on the spine. So here's a shift operation. Suppose you have a bunch of balls. I've drawn them different. Here's a ball, 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 balls. The shift operation is to pick a ball, like this red ball, a red round ball right there, and shift. Shift operation is always to the left. I go to the left some number of steps, and I pull with it all the balls to its right, come along with it. So notice those green bracketed balls move along with it. And when you just shift at a ball, you don't shift anything left. So the stuff, purple, squiggly bracket, and everything left of it stays still. And the rationale for that is the idea is our process is going left to right, covering things. We're going X1, X2, X3, and so on. So the stuff over here, I will have already dealt with. I don't want to upset whatever I've done there. It's already dealt with it. If I start shifting things there, I might destroy some covering there. So when I shift, I only move the balls over to the right, which I haven't covered those yet. Okay, so it's a shift operation, just pick and move. And I think I have an example here. Here's an example shift operation, and see what one of the uses of it. So suppose you shift at that round red ball. Notice right now, if you think of X1 is a root vertex. You think of it, I think of it as having a height 2 tree there. Well, right now in the top one, it's not root covered. But if I shift the red ball over 2, right, 1, 2, now it is. It's centered there. It's now covered. And notice that when I shift it, I pull everything else with it. Notice I leave the ball, this left ball, this blue ball on the left, doesn't move. So now, great. This is how you could use a shift operation. I moved it over, and now I've covered X1. But notice after I've done that, now X2 is not covered because it's right at the edge of this ball. Center's there, so it's there and there. So if I shift it over that blue ball over 1, now that one's covered. So by 2 shifts, I was able to move this over. And notice I'm also making this spine shorter because the thing, remember we start with this path up here, we added on, say, 3 things to that path, and we shifted over a total of 3. So we covered the spine is still covered. So that's a shift operation. And you might, and I was able to just do a couple of shifts and use that to start with the path and cover my P caterpillar, a 2 caterpillar in this case. So second fall stream, you just shift your way to the BNC. Just do a bunch of shifts. There are a few problems. This is a smaller one, I guess. What so much about it. is a tiny ball problem. In the last picture, what if the right leg was of length 2? Let me go back. So here, this shift covers that one because it's only length 1. What if this had been a length 2 one? A length 1 ball, a radius 1 ball could not have covered that. It's too small if it's on the spine because it only goes down 1. So one problem is this issue of if you're doing, say, 7 caterpillar, the balls of radius less than 7 might not reach down far enough. So this one issue is a tiny ball issue, which is a technical thing we have to deal with in the paper. But there's another, and our approach is basically to take those tiny balls, which are a bit problematic, and just move them someplace safe. That's what we do, so they don't interfere with the shifting. Okay, but there's another problem, maybe the bigger problem. Problem 2, why you can't just always shift, is this we call right being right bend. So look at this vertex. Suppose this is the one we have to cover, and its length is only 2 things hang down off of it. Well, I can't shift the blue ball. I don't want to shift. I need to shift the ball to its right onto it. So look at this red ball right here. I have to move it 1 just to get it so it's over there. Then 2 more. I need to shift it 3 times in order to cover that one. And then I have to shift this one once. So in fact, what's gone wrong here is I've no longer covered the spine. Notice the spine of my final caterpillar is only 3 less than this one, but I wound up shifting 4. So I've actually not covered the spine anymore. I've done too much shifting, and the balls are now too far over, and the spine vertex is not covered. And the problem is it's right bad. Let me have a picture of that also to emphasize. Right bad is a sort of a root vertex is right bad is if it's at the right end of a ball. And so you need to pick a ball to its right and move it over, which requires more shifts. So I'm just sort of going to count what's going on here. Why this fails here is there's like an accounting problem. You can think of, remember, our strategy is you have this is your caterpillar right here. You create a path. So this caterpillar has 1, 2, 3, 4, 5 vertices off the spine. Your path is this 1, 2, 3, 4, 5 vertices off the spine. So when you're shifting, you can't pass. You start with a cover of this path. As you're shifting things to the left, you're covering less of the spine. If you go past this point, right here, do not pass line, you've actually not covered the original spine of your caterpillar. So when you're doing the shifts, you better not go shift too many times. In fact, you can see the number of times you're allowed to shift before you covered the spine is exactly the sum of these heights. Height 2, height 1, or number of vertices. 2 vertices, 1, 2, so it's 5 vertices at the end. You can't shift more than 5 times, otherwise you've lost your cover of the spine. So, and this issue of left bad, let me emphasize the left versus right bad thing we saw on the example. So, if you're left bad, in other words, here's your root vertex, a tree hanging off of it right there. Left bad means you're too close to the edge of the ball, right? So if this is H vertices, height H, you're less than H away. So this ball, which is centered, say, over there somewhere, so zip doesn't quite cover the bottom of this right here. So, but this is not as bad. You just need to move a little bit, this ball it's in, move it a little bit over, and you're good. In fact, the worst you would have to do is move it about H over. So however long this is, the worst is you move it H over. If you're right bad, you might need to move it extra. So here's a picture of right bad on the right side. So if you're right bad, that would mean your root vertex is too close to the right end of the ball. Your center is over there. We don't want to move. If you move this, shift the red ball, it's not going to help you at all. So we want to instead shift the purple ball. But the reason it takes more shifts is even though this is only H vertices here, it takes me up to H vertices to get it just over. So it's right at has this right there at the edge of it. And then you can do maybe H more to get it in the actual ball. So maybe do up to 2H, even though this is only H vertices here, maybe you can do up to 2H to cover that vertex. With small gas, but I don't know. I mean, left bad, right bad, shifting. So the shift, okay. So I think I said, oh, end of shifty dream. Yeah, the end of the shifty dream is basically the problem is right bad. If everything is left bad, you can just shift. Because all the accounting is fine. The problem is the right bad take extra shifting. So that's end of the shifty dream. You can't just shift your way to the BNC. New operation, second operation, jump operation to the rescue. The jump rate operation is this. Just an example. Suppose you have a path right here. The jump is I've taken this, for example, suppose you're in this situation here. And like, well, how do I deal with this one? In fact, this is a jump. Take this yellow ball, move it to where the blue ball is, and move everything forward to the right. That's what we call it. By jump up, so we don't consider this a right shift. So the jump up and the jump operation, you take this yellow ball so that it starts at the left end point is at the same place as the blue one was, and put it there. Then you push the blue ball, so it's right there. So notice it covers as much of the spine as before, but it's now covered this vertex right here, that off spine vertex. So just the schematic of the jump operation, you have your balls up here on the top, and there might be a ball way over to the right. Pick that green ball over to the right, and you say jump it to where the red ball is. So they're going to start at the same. So the green ball now starts with the red ball started. It's left end point, and the red ball moves over, and everything else moves over. So you cover exactly the same spine vertices. It might change which things you cover down off spine vertices, but cover exactly the same spine vertices. You haven't also, with shifting, you sort of lose some on the right. You haven't lost anything on the right. So let me discuss a little useful to bring in this idea of called excess. Hey, Nadia. That's okay. It's being recorded. Don't worry about it. So the excess will help us keep track of some things. Basically, the idea. So again, our process is as usual. We start off with some caterpillar, make it into a path. We sort of say the excess is 0 to start with, and as we move things along, the excess is essentially how much extra on the spine we've actually covered. So excess 0 means you've just covered all. So T1 is we move back over some of the vertices to the first root vertex. We move over two vertices here, and we move it 2 this way. Our excess is still 0. If we moved over 2 and only moved it over 1, our excess would be 1. So excess is how much extra on the spine you've covered. We start off with having nothing extra. So we want to keep the excess positive. If excess goes to the negative, it means the stuff on the spine we've now missed in our covering. And I have a example here. Okay, example coming out. So the idea is your excess is essentially when you go from here to a path. There's H1 vertices here. You put H1 at the end. Put H2 at the end. You put all these number of vertices at the end, and the excess is essentially all that stuff minus the shifting. So as long as you want to keep your shifting less in total than the number of things you moved over. That's in order to keep things, the spine covered. I'll give an example of that right here. So, so I'm actually going bottom to top. So you think of the top thing, T3 is the original caterpillar. You create the path at the bottom, and you have a cover on that one. And now you want to root cover all the things. So first we get X1. Notice we can just do a jump there. So excess starts off in T0 at 0. There's nothing extra. There's nothing on the spine. Covered everything on the spine and nothing extra on the spine. And we jump the yellow ball to the blue ball to get T1. And notice covered this whole spine of T1 and an extra thing. This vertex at the right end is not on the spine of T1. So our excess is now 1. We've actually we saved it. This jump saved us a bit. But now to get to T2, I want to cover this one. X2, I need to shift this over 1, 2. So this only gave me, this is only height 1, so it gave me 1 extra shift, but I did 2 shifts, so now my excess is down to 0 again. So I went up, my excess went up to 1, but now I went back down to 0. Notice that in T2, I've covered exactly the spine, no extra stuff. And finally, in this, to get from T2 to T3, it's a 1 shift. The 1 shift matches the 1 vertex, so the shift and the number of vertices match, and the excess stays at 0. So in this process, we want to maintain excess 0 or bigger, non-negative, so that we always cover the spine. Let's see. Here's an example. We increase it. So the good thing about jumping is we increase the excess by jumping. Sort of saw that bit just in the previous slide of it. And because it's 0, we jump. Since it covers exactly the same spine, great, we've got the excess has gone up 1. So let's see. So this is how we're going to sort of use a rough idea how we use jumping. Okay, so suppose you were in the future, this is going to be right bad. For the right bad, you have to do more shifts than you want to do. And this is like, say this is 1, 2, 3, 4, 5. So you need maybe 5 extra shifts than you want. Well, what you could do is look at earlier things like these. Remember, jumping keeps excess, it keeps exactly the same part of the spine coverage. So I could do jumping to cover this, excess goes up 1. Jumping to cover this, up 2. Jumping to cover this, up 2 more. So I got, great, I just saved myself essentially 5 shifts by jumping. The jumping keeps the same part of the spine covered. And now I can use that excess to shift here. Is back down to 0 or something. This is the jumping brings in this extra excess that can use for future shifts is the idea. Let's see, I think okay, so any questions on the jumping and the excess? I don't know. Water. So third fall stream, jumping to the BNC. Why not just jump at every root vertex? I sort of said how, well, if you jump, it's almost for free, just cover it, right? Just jump that thing forward. It covers as much of the spine vertex as it did before, and it covers the root vertex. Just jump all the way, and there you go, it rearrange things. The point is jumping costs you. Requires larger balls to have on the right. Okay, that's the thing, and it's going to cost eventually kind of costing you too much. So you can do it so much. All right, so let me say some words about that. So if you look at this one, so in jumping, you could think of two problems you want to resolve, either a right bad situation or a left bad. So right bad, and right here, the root vertex X up there, and it's too far to the right of a ball. So how you can use jumping is take a bigger ball on the right and jump it so it starts at the same place the green one, but since it's bigger, it now moves farther over, and now it's X is sort of more in the center of the ball, and it's now covered. So if you take a big enough ball, how much bigger should it be? Well, if in this case P caterpillar, you might have at most P things hanging down. In fact, if you notice, every radius increase of 1 makes your ball cover 2 more things. Just if you have like a radius. Here's a radius 2 ball. Covers those 5 vertices. But if you go to a radius 3 ball, this one there at center, 1, 2, 3, 1, 2, 3, it covers 7 vertices. So making a radius go up 1, you actually cover 2 more vertices. So in fact, here, if you're at the very edge of the ball, you just go, and it's at most radius, at least P over 2 bigger, will make it cover move over at least P, and that will be guaranteed to cover your X. In this case, if you use jumping to alleviate a left bad situation, it actually costs you more. If you look at the situation here, suppose your green ball is there, you have your X right there, maybe it has P things hanging down right there. You're too far to the left. Notice if you jump, jumping is always you jump. The jump to the green ball is not going to help you. It's still bad on the left. So jumping here, you can jump, look at the ball to the left of it, that red ball, jump a big ball, this purple ball, so it starts with the red ball, but it's big enough that it goes way over and actually covers X. You see, you're going to need a bigger ball here. In fact, it might need to be radius P bigger. Sort of P over 2 to get you to cover the X, and P over 2 more to get you so that it's in the middle of the ball. So an upshot of all this is the key thing is jumping can cost you up to needing a ball at least radius P bigger. So in this situation, you want to jump, you have a bad vertex you want to cover, you take a radius P bigger ball, get that. Put in the next vertex you want to deal with, you need a radius P bigger. You keep on needing radius P bigger. At least that's why we were doing it. If you could get away with something else, but that's what we're doing. You need radius P bigger every stage. We're using jumping, so that's a pretty big cost. If you don't have a ball like radius P bigger, you can't use a jump operation. So that's the end of the jumping dream. All right. So we can't just jump all our way there. We need the yin yang of shifting and jumping. We need to use a combination of shifting and jumping to get it right. During the process of tree covering, so the easy case, this is back to the shifty dream. If it's left bad, you just shift. If we're left bad, if it's 3 things hang down, you're going to need to shift the most 3. So everything balances out. The problem is a right bad. So if something is right bad, what you're going to do instead is do a bunch of jumps, then a shift. The jumps save you on excess. You're saving up for a bigger shift. So that's it. So the rough approach to the proof is based on these 2 cases. You either just do a shift on a left bad, or if it's right bad that costs you extra, you save up some of the jumps and then do a shift. That's the idea. Okay, so what happens is you just imagine a giant, like the billion size thing. You're going along, everything's fine and vain. You just jump freely, no problem. But at the end, you might get into a problem. So our current root vertex, so all the right balls, sure all the right balls are bigger. So when you're doing this process, you see you're doing X1, X2, X3. We have this cover on the spine. We show that the balls to the right are bigger. So we have a store of balls on the right which are bigger. So to get one with radius P bigger, all we need to do is ensure we have at least P balls to the right. Because if you have at least P balls to the right, well, suppose you want to do a jump. The next biggest one is +1 bigger, next one's +2 bigger, +3. If you have P balls, you get guaranteed to have 1 is plus P bigger. So we just have to ensure that we have, in order to do one jump, we need to have P balls to the right. Then we can just do the jump. So the point is, we just need to have enough balls to the right. And what do we do if we don't have enough balls to the right? Then we can't jump. Then we're not allowed to jump. It's not guaranteed to work. So, well, we get into a kind of situation like this. We're just gonna, if we get into a situation where we can't jump, we're just gonna shift on all the rest of the vertices. Even if they're right bad, it doesn't matter what's going on, we're just gonna shift the rest. So the idea of this is, we in fact start the process. We imagine this giant caterpillar. We start the process, we have lots of balls to the right. We do a bunch of jumping in the beginning. We know we're gonna need to do some shifting at the end. So we do this in the front end, we do all this jumping. So you save up a bunch of shifts. Remember, jumping gives you extra excess. You cover the same spine. And so you sort of save up some. And for this end, we're going to need to do some shifting. That's the idea when we can't do jumping anymore. And there's this dichotomy at this end, which is part of the reason it works, is so at the end, when we're doing this process of shifting, jumping to cover things, well, we either have enough balls to jump. If we have a lot of balls, we just jump when we need to, no problem. If we don't have enough balls to the right, well, what that means is we have few balls to the right, so shifting is not too expensive, right? So either you have a lot of balls to the right, you just freely jump, or you only have a few balls to the right, and all you do is shift for how many balls you have. So if you only have like, here you are, and say you have a bunch of root vertices you still need to cover, we call them all X's. Say you have like, I don't know, a million X's. But if you only have a few balls, say you have 50 balls. All you need to shift to cover, I think, these intersections. You only do 50 shifts, essentially, shift those 50 balls to cover those million root vertices. They're all somehow stuck in the middle. So if you have very few balls, you just need to do very few shifts there. So back to the beginning, just so I get the rough idea here. So in fact, the actual proof has to these two cases. Case one is you have very few root vertices, which is very sparse. In fact, the whole BNC is easy to prove for caterpillars if it's a lot of stuff off the spine. So let's say you have very few root vertices. So it's almost a path with a couple of things hanging off of it. Then our approach is we start in the heavier. That's where you have more vertices. So you cut the caterpillar in half, the spine in half, take the one that has more stuff. Our approach there is we take the heavier half, simply jump to cover all that. And that jump gives you enough stuff to shift on the rest. So you can imagine that if you have your heavier half right here, heavier half, your spine in half is heavier. With more vertices, you save, say, 50 here, and you only have to do, you have 30 on the other side, so you have enough shift to do the rest of the stuff. So you just jump on one half, do the rest of all shifts. The rough idea of one case. Other case is you have a few more vertices, still not that many, but you have more vertices. In this case, we still cut the spine in half, but now we start with a half which has at least half the roots. We don't look at heavier, just it has at least half the roots. And we don't jump on all of them, but we jump on enough. Then in the process of the proof, we're doing shift jump combos. And the point is at the end, we've done enough jumps in the beginning to save up so you do shift when the jumping fails. So the idea there. Proof recap with an animating, well, some pictures stolen from Margaret Ellen. Right? Any nice pictures in here were taken from her. Oh, I should say, I stole, with her permission, nice pictures. The nice pictures were done by her. All right, so here's one there. Okay, suppose you start with your, this is sort of a proof recap. Here's your caterpillar you wanted to cover with the balls. Or what you do first, you convert that caterpillar to a path, and you by putting extra vertices at the end, right? Cover the path, right? We know what to do with square to bend balls. Then we want to convert back to the thing, the caterpillar. So we stick these vertices here. Then we moved over. This is now covered. We don't care about those. Those are off the, not part of the caterpillar. So care about them. But now we come to the next one right here, and we adjust the cover. There we go. We shift that over. Doesn't cover these last two. That doesn't matter. That's not part of our original caterpillar. Oh. And we have now converted the cover of the path into a cover of the caterpillar. Two caterpillar here. So it's just repeating the main theorem, which I outlined here, the proof, right? For any fixed P, this was the idea that P was fixed because we took the end to be really big. The key thing in the proof was end is really big, so you can do some of the stuff I was talking about. That's a detail of the proof. B and C holds for all P vertices. So just a note, there's an existing result which has a 1 plus the low 1 in there. So it's not sufficiently large end result. And you always have a little constant hanging around, but that's another result. Previous authors. All right. So shortcomings of the proof. Well, one shortcoming is only spine cover. In fact, all the balls are centered on the spine, which is, and when it's really big end, it's like you have very small things hanging off of it. So that's why it works. So somehow, so other shortcomings, we probably be more efficient in how we cover. And probably if we want to really prove the BNC, we probably need to venture to put the balls off of the spine, but we didn't do that, which is why we didn't get the full BNC. Could be better accountants. We would obviously like the suburb is floppy, probably if we're not best accountants, probably could improve some of these numbers, being a better accountant, and maybe proving it outright for like P equals 3, 4, something like that. It's known to be true for P equals 1 and 2. Probably if we were better accountants, we think we could probably get it for P equals 3, 4, but we just stopped. Okay, we're submitting that. We're done messing around. So conclusion, yeah. So can we improve it for P equals 3 or 4? Probably with some work. This would be much harder. If we improve it, not for the DNC, probably needs to do some other clever stuff. This paper on the archive, any week now, this is the same thing I wrote a month ago. I gave a talk a month ago. I just left it the same. On the archive, any week now. Okay. I think that is it. Right. Thank you. Should I turn this off? Let me stop recording. Recording is stopping. Let me just, whoops. Right, yeah. Whoops. Oh, you could, I guess, oh, there's a recording. Unrecord it. There we go.